I was 21 years old. I had never published a single paper, and I was about to stand in front of Albert Einstein and tell him his ideas about physics were incomplete. Princeton, 1940. My advisor, John Wheeler, had asked me to present our new theory at a physics seminar. I said yes without thinking. Then I found out who was coming. Albert Einstein, Wolfgang Pauli, John von Neumann, Eugene Wigner, Henry Norris Russell, the greatest minds in physics, all in one room, waiting to hear what a nobody from Far Rockaway had to say. Let me tell you how I ended up in that room. I grew up in a small town at the edge of New York City, Far Rockaway. My father sold uniforms for a living. Nobody in my family had ever been a scientist. He had a gift. He knew how to make me curious. When I was a boy, he would take me for walks in the woods. We would see a bird, and he would say, "That's a brown-throated thrush. In Portuguese, they call it bom de peda. In Chinese, it's a chungling. In Japanese, a kata no takeda." Then he would pause and say, "You can know the name of that bird in every language in the world, and when you're finished, you'll know absolutely nothing about the bird. You'll only know what humans call it. Now let's look at what the bird is doing." That was my first lesson in physics. The difference between knowing the name of something and understanding it. By the time I was 11, I had set up a laboratory in my bedroom. I fixed radios for the neighbors. I taught myself calculus from books. I was obsessed with figuring out how things worked, not just memorizing facts, but really understanding them. When I finished high school, I went to MIT. 4 years later, in 1939, I graduated with a bachelor's degree in physics. That same year, I took the entrance exam for graduate school at Princeton. I scored perfectly on the physics section. No one had ever done that before, but a perfect score on a test doesn't mean anything when you're standing in front of Einstein. I arrived at Princeton in the fall of 1939. The campus was beautiful. Old stone buildings, quiet courtyards, professors walking slowly through the autumn leaves. But I wasn't interested in the scenery. I was interested in physics. And at Princeton, physics meant one thing: the Institute for Advanced Study. That was where Einstein worked. That was where the greatest minds in the world came to think about the deepest problems in science. I saw Einstein sometimes, walking across campus in his old sweater, his white hair going in every direction. He looked exactly like the photographs, but there was something else about him. A gentleness, a quietness. He would nod at students as he passed. Sometimes he would stop to feed the squirrels. This was the man who had rewritten the laws of the universe. In 1905, he had published 4 papers that changed everything we knew about space, time, matter, and energy. He had shown that space and time were not separate things, but woven together into something called space-time. He had shown that mass and energy were the same thing, related by the most famous equation in history, E equals mc squared. And then, 10 years later, he had done it again. His theory of general relativity had shown that gravity was not a force pulling objects together, but a curvature in space-time itself. The sun does not pull the Earth toward it. The sun bends space-time, and the Earth follows that curve. Einstein's work was so profound, so complete, so beautiful. How could anyone add anything to it? I was terrified of him. Not because he was intimidating. Einstein was the opposite of intimidating, but because his shadow was so large. How could a 21-year-old kid from Far Rockaway possibly have something to say that Einstein hadn't already thought of? Then I met John Wheeler. Wheeler was only 7 years older than me, but he was already a professor at Princeton. He had worked with Niels Bohr in Copenhagen, at the center of the revolution in quantum mechanics. He understood physics at a level that most people could only dream of. But what made Wheeler different was his willingness to take crazy ideas seriously. Most professors wanted you to learn what was already known. Wheeler wanted you to question everything. He wanted you to imagine what might be possible. and I had a crazy idea. I had been thinking about a problem that had bothered physicists for decades. It was a simple question, really. When an electron accelerates, when it speeds up or slows down or changes direction, it radiates energy. It gives off light. We have known this since the 1800s. But here is the puzzle. How does the electron know to recoil? When you fire a gun, the bullet goes forward and the gun kicks back. That is recoil. But with an electron, the radiation goes outward into the future. It has not hit anything yet. So how does the electron feel the kick? The standard answer involves something called self-interaction. The idea was that the electron interacts with its own electromagnetic field. It feels its own radiation, and that is what causes the recoil. But there was a problem. When you did the mathematics of self-interaction, you got infinities. The equations blew up. They gave you answers like the energy of the electron is infinite, which is obviously nonsense. An electron sitting on your desk does not have infinite energy. Physicists had been struggling with this problem for years. They had tricks to get around the infinities, ways of subtracting one infinity from another to get a sensible answer. But these tricks felt like cheating. They were not a real solution. I had a different idea. What if the electron does not interact with itself at all? What if instead, the electron interacts with all the other charged particles in the universe? All the electrons, all the protons, everything with an electric charge? And what if those particles, when they absorb the radiation, somehow send a signal back through time to the original electron, telling it to recoil? Signals traveling backward in time. It sounded completely insane. But when I worked out the mathematics, something remarkable happened. The equations balanced. The infinities disappeared. The theory actually worked. I brought my idea to Wheeler. I was nervous. I thought he might laugh at me, or tell me I was wasting my time with nonsense. He did not laugh. He listened. He asked questions. He saw something in the idea that I had not fully understood myself, and then he started helping me develop it further. We worked together for months, refining the theory, checking the mathematics, looking for flaws. We called it the Wheeler-Feynman absorber theory. It was unconventional. It was strange, but it was consistent, and it made the same predictions as the standard theory without the infinities. When we had something solid, Wheeler said the words that changed my life. Wheeler said to me, "Feynman, you are a young fella. You should give a seminar on this. If you're finding this story valuable, consider subscribing. I tell stories about the moments that shape the greatest minds in physics, the moments they do not teach you in textbooks." The day of the seminar arrived. I walked into the room early and started writing equations on the blackboard. My hands were already shaking. I was holding my notes, and I could see the paper trembling. I can still picture it. The envelope, my handwriting, the slight vibration that I could not control. Then the door opened. Wigner came in first. He was the one who had organized the seminar. Then von Neumann, the Hungarian mathematician who could multiply 8-digit numbers in his head, who had helped invent game theory and would later help design the modern computer. Then Pauli walked in. Wolfgang Pauli, the Austrian physicist with the sharpest tongue in all of science. And then Einstein walked in. He came up to me before the seminar started. I was standing at the blackboard, chalk in my hand, trying not to panic. He said hello in his soft German accent, and he told me he was coming to my seminar. Albert Einstein had just introduced himself to me, as if I did not know who he was, as if we were colleagues, as if we were equals. I don't remember exactly how I started the presentation. I know I explained the problem, the infinities, the self-interaction, the puzzle of radiation reaction. I know I described our solution, the absorber theory, the idea that signals could travel backward in time, and the mathematics that made it all work. As I spoke, I watched Einstein's face. He was listening intently. His eyes were focused. He was not checking his watch or looking out the window. He was following every step, considering every argument. The presentation continued. I covered the technical details. I showed how our theory made the same predictions as the standard approach. I addressed the obvious objections, Yes, it sounds strange, but the mathematics works. When I finished, there was silence. Then Pauli spoke. "I do not think this theory can be right," he said in his thick Austrian accent. "Because of this, and this, and this." I don't remember exactly what his objections were, but I remember what happened next. Pauli turned to Einstein, who was sitting right beside him. "Don't you agree, Professor Einstein?" This was the moment. Pauli was the great critic, and he was asking the great Einstein to confirm his criticism. My theory was about to be demolished by the two most formidable minds in physics. Einstein paused. The room was silent. Then he said one word. "No!" It was a long, drawn-out, very German, no, polite, but firm. "I find only that it would be very difficult to make a corresponding theory for gravitational interaction." Einstein continued. He meant that it would be hard to apply our approach to his own theory of general relativity. Then he said something I will never forget. "But after all, general relativity is not so well established as electrodynamics. I would not use that as an argument against you. Perhaps we can develop a different way of doing gravitational interaction too." Do you understand what had just happened? Albert Einstein, the most famous scientist in the world, the man who had invented general relativity, had just said that his own theory was not so well established. He had just suggested that maybe, just maybe, a 21-year-old graduate student might be on to something that could change how we think about gravity itself. He didn't say I was right. He didn't say our theory was correct. In fact, history would prove that the Wheeler-Feynman absorber theory never became the standard approach. Pauli may have been right about some of his objections, but that wasn't the point. The point was that Einstein took me seriously. He listened. He considered. He defended my right to propose new ideas, even ideas that challenged his own work. That is what it means to be a scientist. Einstein and I never met again. He was in the sunset of his career. He would spend his remaining years searching for a unified field theory that always eluded him. I was just beginning. Our paths simply did not cross. But I carried that day with me for the rest of my life. Years later, when I developed my own approach to quantum electrodynamics, including Feynman diagrams and path integrals, and the work that would eventually win me the Nobel Prize, I thought back to that seminar at Princeton. I thought about how Einstein walked into the room and introduced himself to a nobody. I thought about how he said no to Pauli when it would have been so easy to say yes. I thought about how he kept his mind open, even at the end of his career, even when young people challenged ideas he had spent his life developing. That is what I learned from presenting to Einstein. Not a physics formula, not a mathematical technique, something more important. I learned what it means to be a real scientist, someone who cares more about truth than about being right, someone who listens to new ideas, even when they come from unexpected places, someone who says perhaps instead of impossible. Einstein took me seriously before I had done anything to earn it, and that made all the difference. I was Richard Feynman, and I was just getting started. If these stories resonate with you, subscribe and join me for the next one.